Good morning, everyone. Thank you for coming to my session out of the 4 sessions that are run concurrently. How many of you are developers or architects? Good. Because it's going to be a development session. I'm going to talk about how to build key things we have to know about building scalable applications on top of SharePoint 2013. And first of all, I would like to thank the sponsors who make this event possible, the community event, especially the SharePoint Saturday. And if it wasn't for them, we wouldn't have the first SharePoint Saturday in Stockholm. As for me, my name is Edin Kapic. Thanks to Unicode, I can write my name properly in almost all the all the formats. And luckily for you, the Swedish guys, you know this letter from Ibrahimovic. We had a and I come from Bosnia and Herzegovina, but I live in Spain for 20 years, and I work in Barcelona, where we are hosting the European SharePoint conference. And my Swedish is a little bit rusty, but I think that I can say that jag skulle vilja träffa alla i maj i soliga Barcelona för den för den European SharePoint conference. Kommer ni? Okay. Thank you. It doesn't come much more than that. I work for a company called Spenta. We are most known as the maker of the social network for SharePoint on-premise, not like Yammer crap. It's called Busy, and I'm SharePoint Server MVP since last year, and I also run the Catalonia user group for SharePoint, which we do some events locally, and we'll be doing some things for the European SharePoint conference. You can find me on Twitter, you can find me on my blog, and you can also find me here today, and you can mingle. Okay? And as you can see, I always look at the fine print, even if it's on a on a bottle of beer, because we'll have a SharePoint later, so I had to inspect the quality of the of the liquids. Okay. The topic of my talk is scalability. The dictionary says that scalability is the ability of something to adapt to increased load. Wow, that doesn't help us very much. For me, the definition of scalability is when you have good news and bad news, and how do you react to them. The good news is that your new app is going to have 1 million users. Wow, that's good news, 1 million users in revenue. The bad news, they all sign up tomorrow. When you say this to your boss, or the chief architect, if his face is the left one, your application is scalable. If his face, if it's left one, it's not scalable. If it's right one, if it's like this, then it's scalable. So my objective is for you to have your apps in this mode, the cat in the windowsill. Okay, enough fun. What happens when scalability is not taken into account when launching an app? Simpsons tapped out. Everyone has heard about this application? The official Simpsons game for tablets and mobiles. It launched without scalability testing. And it was plagued with these errors. Server is busy, try again. Server is busy, try again. They had to remove it from the store, then relaunch when they fixed the scalability issues, but it's, I think it's not available anymore. This was a huge fail. And the good one, draw something. You know this game? You draw something, somebody has to guess what you're drawing. They launched in February with 3 drawings per second, 5 million transactions in total. And in 1 month, they had more than 5,000 drawings per second and more than 2.2 billion stored games. And the latency went from 0.5 to 0.9. For me, that's very good scalability. And they have a nice white paper where they explain all the technical stuff, how they did the architecture, how they scaled out without shutting down the servers. And they went from 6 servers to 90. Of course, that's the price you have to pay for scalability. You have to add extra hardware, but you have also to change your architecture. So it's recommended reading if you want to go deep in the scalability issues. So this is scalability about in general, but what happens with SharePoint? In SharePoint 2013, we have the new app model, the brightest and shiniest and newest app model, which is going to be the best development model ever. promised by Microsoft, but it's cloud-based. Of course, I don't count as SharePoint App Model the SharePoint SharePoint hosted apps. It's just JavaScript on the client. But for the real apps, we have basically two options. We have auto-hosted, auto-magically provided by Azure, or provider-hosted. For me, the real choice is this one, because you can connect to the services you would like. You can use Azure services, extra services, not only the websites and SQL Azure, like here, but you can plug in to any services you would like. Okay, I'm going too fast, too slow. Okay, don't hesitate to interrupt me in any moment. So the first lesson with SharePoint and scalability is that we are disconnected from SharePoint. SharePoint, for all instances, is just another external system like the database, the cloud, or third-party API. So minimize round trips. When you're traveling, it's a good option to have round trip, but when using apps in SharePoint, when designing them, try to minimize the number of round trips, because every query to SharePoint is one query outside of your system. So if you allow me to go for a second to a galaxy far, far away, what can we learn about scalability from Star Wars? Okay, I love that look. What's going to come? Well, the lesson is, with the cloud and with the apps, we have the potential for scalability and high availability. So the cloud is sold as it's going to solve your scalability issues. That's only half true. It's a potential to solve it, but you have to architecture for it. It doesn't come out of the box. It didn't come out of the box from the Death Star, because when it was being designed, the chief designer was ensuring the emperor that it's going to be resistant to all possible attacks. And we know how it ended in Battle of Yavin. Single point of failure, right? The core reactor. And the chief architect was really angry. He found the lack of failover really disturbing. Okay, now back to our regular program, okay? When you design a SharePoint 2013 app, chances are that you will come with something like this. You have your SharePoint browser pointing to an instance of a site or a virtual machine in Azure. You will have your ASP.NET or MVC layer. Then you will have a couple, 1, 2, 3 business layers. Then you will go to data. So 3-tier, 4-tier, depends on how complex your logic is. This is not scalable, but it's simple. So in this session, in the 40 minutes, 45 minutes more or less, we have taken into account the questions. I will try to let you get this. This is the summary slide, so if you want to shoot, wait until it's all on the slide. And if you have to remember one thing from this session, is this one. 3 main things to avoid when planning for scalability. Avoiding round trips. We have seen that slide. So we have different mechanisms to avoid round trips. So you don't go to other servers unless really necessary. The second one is avoid any bottlenecks. If you have to pass through one single point in your system, which can make other requests to be held, so try to design around that. So we can see some how we can overcome storage logs, how we can queue requests, and how we can do some async stuff. And the third thing is avoid single point of failure. Avoid being the Death Star. So do redundant design whenever possible. So this is the summary slide. It's going to be repeated in the end, and I've included this extra ribbon around it because when I go to technical sessions, I really like those one-slide summary, so I can then explain to my colleagues. I've been there, and this is what I learned. So, remembering the non-scalable app, we have the scalable app here. So basically, we separate the user requests. They're going to be served by the web roles, and then we have other servers which are going to do the business logic, and we connect them with different Azure services, and we can also use different kind of storage for different purposes. We can also leverage CDN. I'm going to explain, this is what I'm going to explain in this session, and this is how different strategies apply. With those technologies, we minimize the round trips, we minimize the bottlenecks between different components in the overall application, and everything is redundant. We don't have single point of failure. This is the scalable app. So, still with me? Let's go to see the first mechanism, caching. It has been around since the beginning of programming. The caching is still the cheapest way to save round trips. You read something, you store it close to you, and then you don't have to read it again in the original source. It's cheapest, and it's really simple. We have two kinds of caching mechanisms in Azure, or basically in almost every cloud environment. We have a local cache, which is local to the machine where we are running our code, and this is where we store static data. So, things like the list of countries. If you are doing something about shipping, you have the list of all the countries you ship to, and it doesn't change from one day to another, right? It's fairly static. So just cram it in the cache and never read it again from the database. Just keep it like for a year there in your cache, and you save that query for every possible Dropbox you're going to fill from to your interface. So something that's really small because the amount of local cache is limited, and it has to be frequently accessed, like those drop down lists that we fill. What happens when we have to cache things that have to outlive our local process? We can use distributed cache. Azure comes with distributed cache mechanism, and my rule of thumb for scalability is that put in cache everything by default, except when something doesn't warrant being in cache. So by default, you should put it in cache, because it saves round trips. And the problem with distributed or local cache is always stale data. What happens when the data we have in cache is not the latest version? Well, we have different strategies around it. We can flush the cache when we update something. We can architecture around that. We can also use shorter time window for the cache expiry time, because when we put something in cache, we can also put the expiry time. And sometimes it's acceptable to have a little bit of stale data and have more scalability. It's kind of a trade-off. In some applications, it's not an option, because it has to be critical, in the second that the data changes, you have to expunge all the stale data, so it's your architectural decision. But mostly, for the end user, it doesn't care if the data is like 10 seconds out of sync or 30 seconds. We are not really that picky about data. Let's take the cache idea one step forward. We have content delivery networks. You've heard about them? Okay. Basically, what we have in Azure, we have a blob storage where we can store anything binary. Files, documents, pictures, anything. It's a big storage in the cloud. So one of the frequent operations we can do with the blobs is we store the blob, then we read from the blob and present it to the user. Usually, you will do this like reading from a local file. You read the binary data, and you pass the binary response to the user. But in case of blob, what you can do, you can directly bypass the processing, so you just point the user to a URL to the blob. Okay? You following? So your application doesn't get the blob and present it to the user. You just point the URL, and when the user clicks to something, it goes directly to the blob. It bypasses your application, less scalability problems. Of course, the URL has to be public. What happens when you don't want to allow users accessing blobs, which are public? For instance, it's a copy of a scanned contract for one customer. So you want only that customer to have access to the blob. You can use a thing called share signatures. It's a special URL appended to the end of the blob URL, which identifies
the permissions for that file. So if you have this URL, you can access it, and it expires. It's similar when if you use SkyDrive to share files with people. Sometimes you have this option to share the file with someone by email, and it constructs a really ugly URL. This is share signature. It's the same mechanism the SkyDrive uses. Okay, so the first thing about Blob is that you can think about bypassing directly if you don't have to do anything with a Blob, just serve it to the user, you can bypass your web presentation entirely. And one step forward, you can also cache the blobs close to the user. The CDN are those different centers run by our Azure team where the data is cached close to the user. So you can have your data in an American data center, but it can be replicated to all those CDN servers, and then when your user from Japan accesses the blob, for instance, when you release an update, you have to update a bunch of binary files, so you just release them to CDN, and they're going to be served close to the user with less latency. So offload anything you can, images, scripts, media files, almost everything that's binary. What happens when you want to update and your CDN copies are stale? For instance, JavaScript. You update the JavaScript, and then the CDN cache is the old version. You can do the trick using versioned URLs, which means you append a parameter to the URL, which is unique. For instance, version, v equal to 1, equal to 3, and the CDN caches by the full URL. So it's not going to cache your new version. You just update the URL in your application, and it's going to force the CDN to get the new version directly from the blob storage and copy it to the rest of the nodes. I see a little bit like with face, what is talking about? You're following along, or I'm going too fast? Okay. So the first thing, round trip mechanisms, how to avoid them, use cache or offload, use blob storage or use CDN. One of three things. The second thing was the bottlenecks. One of the strategies for reducing bottlenecks is avoiding storage locks. What's a storage lock? This. When you go to the bathroom in an airplane and somebody is inside and you have to wait, it's storage lock. They are using it in write mode and you can't even read because it's blocked. You can't access the shared resource because it's being used by another process. Let's put it in this finer way, right? And this is a storage lock. We have it anytime we use relational database. So we have to make a choice. Sometimes we have to use a relational data model. It's something we feel comfortable with, but the price we pay is that anytime somebody updates relational data, all the reads have to be put on hold, more or less, depends on the concurrency level of your SQL Server, because you can't let people get data because they are pending to be overwritten. So sometimes we should use another NoSQL model, which doesn't guarantee the relations between the different entities. So sometimes it's okay, because you only need to store something and access it again. And it doesn't matter if there is another copy with different data. So in Azure, we have two storage mechanisms. Relational one, SQL Azure, and non-relational one, NoSQL storage, table storage. Table storage is basically, it's a repository for a collection of key and value entries. Like a dictionary, and you put a collection of key and values, and it stores as a single row. So it's not table, but it's called table storage, but they're not SQL tables. They're just key values collection. And the price we have to pay, everything comes with a price in life and computer engineering, is that in relational data model we have immediate consistency, which means that and any moment, the model is consistent. So all the updates are done in a consistent fashion. There is no disconnect between the update and the subsequent read. But in a non-SQL world, we have eventual consistency, which means eventually it's going to be consistent, but not immediately. So during a short period of time, you're going to have either stale data or two versions of data at the same time. So you have to overcome this in your application layer. So you have to design for it, and the reward is that this is much more scalable than this by nature. So if you have to store some data, think by default how to store it in table storage, and if it doesn't work for you, then use SQL Azure. Of course, this is only valid if you have a huge amount of data, like millions of users. But if it wasn't the case, you wouldn't be attending a scalability session, right? Okay, you heard about CAP theorem, from a database design. Basically, it says that when we are storing data in a computer system, we have to pick 2 out of 3 options. We either have consistency all the times, we either have high availability, which means we are tolerant to balancing, or partition tolerance, which means that if we split our servers in 2, they are still the data is still has the same shape and it's still consistent. So pick any 2 of them, because in relational data model we are not partition tolerable, but we are available and consistent. In the non-SQL we are not consistent, but we can be partitioned, because in NoSQL we can duplicate anything, and we have high availability. So it's always pick 2 out of 3. We can't pick 3 of those properties and use them. So this is one strategy. Just choose your data model. It doesn't have to be SQL. You can use NoSQL. It's much more scalable, but sometimes you have to use SQL. Even if you have to use SQL, you can do sharding. Sharding is the technique of separating your huge database in a bunch of smaller databases. And when you have to write or read something, you consult a partition key, which is one or a couple of columns, which are the key for which database it will go. Usually, to be simple, for instance, a country. You can make one database for each country where you're operating, and all the transactions go to the database for that country. It's still the same schema replicated in all of them, but you have like one database per each country. So it's more scalable because you can update Italy while reading from Spain, or you can do joins across the different shards. It's a little bit tricky to do joins across different databases. Basically what you do is you parallelize your query across all the databases that then you join in memory. In Windows Azure, you have this SQL Azure Federations capability, which is basically the commercial name for sharding in SQL Server. You can federate different databases based on partition key you define. So it's worth having a look if you have to stick with a relational database model. If you want to take this idea of separating data storage for different purposes, you can also look the CQRS, or Command Query Responsibility Segregation principle, which is basically an architecture that does 2 things. It has a separate system for queries, which is read-only and highly parallelized and highly denormalized and using cache everywhere, optimized for queries. And then you have a single model of truth, which is the write model. Usually it's relational, and the changes you do here propagate to the read model. In SharePoint, we use this under the cover. For instance, you know the search service in SharePoint. This is the same thing. This is your SharePoint data, and this is the search index. It's a read-only copy of the data, update more or less frequently. It's the same principle, but in SharePoint we call it search server. Or in 2013 we have this content query, content search web part. Heard about it? Content search web part does queries in the search index, and the content query web part does queries here in the live read-write model of SharePoint, where the data is. So the idea here is to separate all your read operations and all update, delete, and commands, which are usually something that changes the state of your model, and channel them to different data storage. That's it. And you can do publisher subscriber architecture here. It's like the evolution of highly scalable patterns for any kind of applications, but in SharePoint we already use this under the cover, so it's worth knowing it. Okay, still with me? Good. Second option, to reduce bottlenecks. You did this, you have done this morning, waiting in the queue to register, right? Sometimes it's not bad thing, because what we have with request response model is that when we issue a request, we are stuck until we get a response. We are more or less stuck. The petitioner has to wait for the answer to come. So it doesn't scale really well, because you have to scale in the number of concurrent requests. But if you can just queue the request, you can decouple the part of your application that does the request from the part of your application that fulfills the request. So what's the idea of having something here in between? Basically, you decouple, so you are not bound to wait in the left side of the diagram. You don't have to wait for the answer. You can just poll periodically for the answer to see if it's already been processed for long-running operations. You can also have messages here. You can also retry. You can reroute them on different servers according to the availability. You can throttle. You can avoid denial of service attacks, because your attacks are not going to block the backend, because they're going to be enqueued, and then you can detect that there's a floating attack, and you can just tackle on a reduced rate of service. And you can also scale up and down. If you see there are many messages in the queue, you can fire another server and process in parallel different requests in the queue. In the Azure, we have two kinds of queue. We have Azure queues. Actually, they are part of blob storage. They are low-level, point-to-point queues. We can pass messages between different nodes in Azure. And we have service bus queues. Service bus is much more high-level. It's a messaging framework, central messaging framework for your cloud. And it's more publisher-subscriber relation, and it's fully transactional. So usually you will choose this one unless you need enterprise rate a message queue, which is this one. Of course, the price is not the same in Azure. And the structure of the queue, more or less, it's like this is the storage queue, the cheap ones. You have your storage account, and then you can build queues. And in each queue, you can enqueue messages. And you will have basically two parts of your application, one writing the request to the queue, and one reading the request from the queue and fulfilling them, usually writing to another queue for the requester to get the answer. Okay? You can ask at any time, maybe it's lack of coffee. I was being told that Sweden is the country that consumes most coffee per capita. So, okay, I like that one. And the third mechanism that we can use to reduce bottleneck is acting asynchronously, out of sync. So I would like to introduce you to friends of mine, two waiters in the restaurant, Mr. Sync and Mr. Async. And the customer, of course. The customer is the king, right? So Mr. Sync is the waiter that comes to the customer, and the customer says, okay, I would like a steak and with a side of fries, right? And he says, okay, yes, thank you very much, sir. Goes to the kitchen, goes to the cook, and he says, I need a dish of steak and fried for the table number 4. And then it sits there looking the cook as he's doing the dish. And then when the dish is finished, he takes the dish to the customer. It's a nice idea to have if you want to reduce unemployment rate in your country. So if you need more concurrent requests, more waiters, no problem. And you have the Mr. Async. He's the efficient waiter. He goes to the customer, he takes an order for the steak and fries, goes to the kitchen, tells the order to the cook, and then puts a sticker that says steak and fries to the table number 4, and then goes to serve another customer. Something that we are used to. It's efficient. But when we are programming, we are the inefficient waiter. We have our web tile with one thread in the IIS serving the requests. We get a request. We send a request to the data tire, and we wait. And then another request came, but it's blocked. We will have more than one thread. By default, in ASP.NET, we have more than one thread. But the idea is that this thread is not doing anything useful. It's just sitting there looking at the data type to come with a response, right? What if we could do it differently? We have a web tire, still the same thread, the same code, receives a request, fetches the request to the data tire, and then puts a sticker saying, I'm waiting for a response for request number 1. And then request number 2 comes in, so I can go there, serve the request, basically passing the request to the data tire, putting another sticker, and now when the data tire replies, I go there and say, okay, who was this for? Request number 1. Here we are. And with this, we can scale much more. Same code, just more efficient. And in .NET 4.5, it's as simple as putting async await around your code. And this is what I would like to show you, a quick example. If the demo goats are with me. So basically, I have a small application in MVC, which is called Stock Controller. You see the okay, I'll put it a little bit more. Basically, I simulate a long-running operation by sleeping for a half second, and then I get the quote, of the stock quotes, back to the user. So this is really simple. And what happens if I try to do this in a concurrent fashion? So let's fire up. I really like the Apache benchmark tool, AB, for doing benchmarking of the code. So basically, I'm going to issue a request, let's say 500 requests with 100 requests concurrent to this address. Okay. This address here, it's an MVC API, web API, so it's stock. It's going to get the JSON data from the backend. And 500 requests, 100 at a time. Be patient. It'll take like 15, 20 seconds. 100 requests done. And we can see some statistics about the length of request. Because I think that by default, ASP.NET has 10 or 16 threads by default. And if you have 100 requests, 90 requests are going to be on hold. And we will see that the response time is growing really fast. Now we will have the results. Basically what it says, we have effective rate of 12 requests per second. Not bad, but it could be much better. 12 requests per second, we are doing 100. We are losing like 80% of it. And the time per request is 7 seconds. And we only have half a second block on the back end. The rest is waiting until the back end is available. But the code is really straightforward. It's nothing strange around it. But I can do it better. I have an async controller. Same code, but instead of having a normal operation like list, get list, I have async task, which returns list. So basically, you replace all your return types with task, generic return type with your information you are returning. You put async, and you await for all blocking calls. Basically, what it does under the hood is that it builds a state machine around it, and it points to different delegates to wait for the answer. The code is still the same. It's cut and paste code from the original stock controller. But if we repeat this same operation, the code hasn't changed. 100, 200, 300, 400, 500. Let's see. 171 requests per second. Still the same code, same hardware, same process. And the average waiting time in the queue is around 580 milliseconds. And we have 500 milliseconds penalty in the code. We sleep for half second. And we only have small overhead. And all the requests are served in the same fashion. For me, this is like an eye-opener. Okay, why I'm not using it? Because previously it was very difficult to do this kind of thing. You had to keep the bookkeeping of all the requests and responses by yourself. But with .NET 4.5, it's a question of putting the async await. But it comes with a warning. This is only good if you are waiting for I/O operations. If you are doing something which is CPU intensive, it doesn't work because the CPU is going to be blocked anyhow. But if you are waiting for something other than the CPU, put an async call and await it, and then it's much more efficient use of resources. And the other thing I would like to show in the demo is this blob storage I was talking about. So I have here, this is an action in MVC which goes to the blob storage, downloads it, and returns it as a memory stream. So it's a photo of Stockholm, right? It's not inefficient, but it's much more efficient if I just give you the URL. The URL is pointing to the blob storage in Azure Cloud. It's much more scalable than my application. So why don't point to this in the first time? So just you can see the code. It's pretty simple. I have it's here. I just get the blob, get the image, and then I do a memory stream and I return it to the user as a stream. But it's inefficient. What I do is I'm shuttling bits from one storage to the response. I can just bypass that. It's much more scalable. Okay. Now, back to our regular program. Again. No. Right. Okay. Really took me some time to do this animation, right? Okay. So the last topic is redundant design. Redundant design is tackling this no single point of failure, avoid the Death Star syndrome. So redundant design basically is the idea that if one of your nodes in the application, whatever, fails, your application is still good to go. Although some delay is acceptable. So it's like, okay, instead of waiting for 1 second, I wait for 10 seconds, but it still works. So here we have redundant power supply. Same idea with the computer. You don't rely on one power supply, you put two of them. So the chances that two of them are going to blow up at the same time are really small. Redundant design is something that Microsoft sells in Azure really good, because they say you can scale your, you can duplicate all your nodes, you can fire as many instances as you would like, but you have to design. You have to do some design changes in your architecture. basically two things you have to do. You have to design your operation to be idempotent. Strange Latin word for saying essentially that it doesn't matter how many times you do it, the result is still the same. It's important because if you don't do it this way, a failure in one of the nodes can be lost, or worse, can be repeated and retried several times. For instance, if the operation is deduct 100 euros from the account, it's best not to try to retry it like 10 times. And you know when you are purchasing something on the internet, it says, do not refresh this page. It's because the operations are not idempotent, which means they don't put some unique information to avoid doing twice the same work. So every time you do updates or you do some critical stuff, you will have to design your operations to be idempotent. So basically, doesn't matter how many times you repeat it, the result is the same. Usually the REST API, if you design the REST API, usually it is, because it doesn't matter if you do a GET operation on one URL, the result is always the same. Do it once, do it 2 times, 100 times, the result is the same, as long as nothing has changed in the back end. And if you do an update, the result is also the same. It's going to be updated to the same state that you put it. It's not going to change. So you'll have to design your operations around it to avoid the retry mechanism. When you are doing some load balancing, maybe you are going to have the same operation retried twice or thrice. Then you have to make sure that it doesn't add different results. The worst result is the money account and deduction every time you do an operation. So you have to be really extra careful about that. And you also have to design load balancing strategy. Could be round robin, could be least used server, most recent used server. There are different strategies. And in Azure, we have a small piece of functionality called Traffic Manager. Anyone heard about this? Okay. It's an extension of DNS, basically. What it does, you have your different services, different copies, different redundant services of your application in different data centers. And you have a table of different IP addresses for those servers, and you have a policy in place for failover, round robin, performance, anything. And then your application has, instead of going directly to those servers, it issues a DNS request looking for the server, and this is intercepted by Traffic Manager, and then it serves the IP address of the closest, the least busy server, whatever. And also, it allows for failover, because you provide Traffic Manager with a URL, which is basically a heartbeat, so it's going to be pinged frequently by Traffic Manager, and if it's not available, it's going to mark all the entry of your server as non-available, and it's going to reroute those requests, outstanding requests, to another servers. So you have to design around that. But it gives you the automatic failover capability. You don't have to build it yourself. It's already included in Traffic Manager. Okay? One can get really thirsty speaking in the sessions. So the redundant design is also used in highly scalable applications such as Farmville. You know Farmville. It was very popular a couple of years ago. And this is the official architecture diagram for Farmville, which everything is redundant. You have DNS, a kind of traffic manager. You have an array of load balancers, an array of web servers, an array of distributed cache, and an array of databases. Everything is one-to-N. And if one of those databases dies, you have master and slave, and you have replicated, and you have replicated distributed cache, you have replicated web service. So it doesn't matter if 1 or 2 server dies, or 3, just spin new ones. Your system is going to adjust. Of course, multiply the number of servers by the cost of the servers. So scalability is not cheap, but it's not as expensive as not having it if you're having millions of users. Okay. So in a nutshell, my 7 key things for you to take away are those. 3 problems, avoiding round trips, avoiding bottlenecks, avoiding single point of failure. 7 strategies, caching and CDNs and blob storage for avoiding round trips, NoSQL sharding and queuing, and async for avoiding storage locks, and redundant design for avoiding dead star single point of failure. If you are really interested in the scalability things, I would recommend, okay, I just leave you to take this. This is going to be published anyway. I will record it, I think. There is an excellent web page called Highly-Scalability.com with a lot of examples of real-world application scalability designs, interviews with the architects and the creators, and overviews, testings, theoretical stuff. It's really, really, it's excellent page if you are into it. And there is also a session on Channel 9 from last year, TechEd. It's called Advanced Patterns in Cloud Hosted Apps for Microsoft SharePoint. It's more or less some of the Azure techniques I have outlined today, but explain in more depth, like how you use them in the code, because for 50 minutes, practically 50 minutes, I couldn't cram so much information in and still expect you to retain some of it in a couple of days. But it's also worth a visit. So question and answers are available for you if you want to ask any questions, and please rate the session, because it really matters to me as a speaker and to the organizers to know what works and what doesn't work. And thank you very much for attending. And if you have any questions, now is the time for it. You think it was interesting? You learned something? Good. That's what I'm really glad to hear about, because it's like just sharing a couple of things and just make sure that people really retain it. Because this is a difficult thing when you plan for a conference. Do you have any scalability issues in your application? Okay. It's how I come up with this scalability thing, because when we were developing our social network for SharePoint, the Busy, and we have this customer with 100,000 users. And when you do a SharePoint development, usually you do it in a, let's say, non-optimized way. And you don't really think about scalability because it's just replicated to the servers. But there are some bottlenecks even in the SharePoint. For instance, the profile. If you are querying profile database, it's a bottleneck. You have to spin several profile instances to be able to do it in parallel, like for 200-300 users at a time. And then we really learned a lot about SharePoint app scalability and SharePoint code scalability in a hard way, serving it to the customer and then fixing the scalability things as they come along. So we learned a lot of that. And we are doing the cloud version of the social network. So we have different kind of scalability issues, but that's where all those topics came from. Okay. Yeah. For SharePoint hosted apps? Well, SharePoint hosted apps still applies the same, you can still apply the same don't do round trips from SharePoint, because you are on a client side in your browser, and SharePoint is on the server, and you have to query by CSOM or REST API. And then you can also use the memory to cache things, but you can't really do much more. It's a simple two-tier architecture. You have request, response. You can't really do much around it. You can layer up your architecture in JavaScript. You can use frameworks to do it like in a much more maintainable way, but it's not going to be much more scalable than that, because your backend is still SharePoint. You don't have any, you can't juggle around it. Well, you will have to analyze. My recommendation is to try to use this approach to identify the operations you are going to do against the data store and try to isolate them from one another as much as possible. So if you have a lot of reads and a couple of writes, separate them to different APIs, different methods, and even to different servers if possible. So you don't have the storage locks, because they are one of the most persistent errors in scalability. It's like you're waiting for something to become available. But good app design really translates to good API design from your side for your backend. Sometimes the API is just what is left public when the program is compiled. But if you pay attention to design your API and then design an application around it, it's much better, because you can infer your API from your operations you need from it, instead of designing it in the first place and then using it. You know what I tried to say. Okay. Welcome. Any other questions? Or you can go have a coffee and a cinnamon bun. Yes?
These scalable architectures that you described,
yeah.
if you use SharePoint lists, data stores, does Office 365 benefit from that architecture?
Well, SharePoint is scalable as a data store, because you can have different servers and you can have round-robin capabilities around. But if you store data in lists, lists are scalable up to a certain limit. You know, there's those limits for items in list and for items in a folder. They're basically they're not hard limits, but it's just as it's going to block you for some time. But if you have too many items in a list, your waiting time for operations is just going to be beyond the threshold, which is acceptable to you as a consumer of that data. So it's not really an architectural limitation, but it's how much of the delay are you willing to accept. So it's not as scalable as, for instance, the NoSQL table storage in Azure, because it's highly replicable, because it's distributed, and there is no single source of information. And in list, you have single source. It's all in one database. Yes?
If you have your data in Azure SQL,
Yeah.
and you have your logic for content delivery network and so on, what is the purpose of a SharePoint app? There is a usual...
Ask Microsoft. Now, usually you will store your app information, or for instance, if you are designing an application that stores, let's say, scanned invoices, you can store invoices in SharePoint, or you can store invoices in table storage or blob storage. So it's like, if I store it in SharePoint, I have those storage limits and performance limits, which are imposed by SharePoint. And if I store it in my data center, in my cloud, in my storage, I can set the limits. So I can play with the limits around. That's the difference.
There is no need to package it as a SharePoint app.
If you are just deploying it to 1,000 users, there's no need to package it as a SharePoint app. If you are doing this as your app as a service to multiple tenants and multiple and millions of users, like that's the promise of SharePoint App Store, right? You publish your applications, and many customers can install them, and you're going to host them in the same data in the same cloud. So you have to design it to be scalable. Of course, if it's scalability comes with millions of users, because if you don't have millions of users, millions of requests, you don't have scalability problems. It's as simple as that. Because sometimes it's an overkill. So if you see this draw something application had 90 servers. 90 servers is okay if you are having millions of operations. If you have just 100 users using it, you are good with one, preferably 2 SharePoint servers, just to having some failover, nothing else. It's always common sense. Okay. Yeah?
What are the methods to do scalability testing on SharePoint? Like, for instance, when you're going for a large-scale investment, how do you make sure that this is going to work?
Well, you do, usually what we do is we load test. We do load testing with as close to real data as possible. So we try to simulate the real user load. There are a couple of tools to do this. And it's, in our experience, it's much better to do the load testing before even architecting the design, because it's like, okay, I'm going just to test the load to the SharePoint. Okay, how many operations? Just dummy operations. Let's see the metrics, and then we are going to design something around it. Because it's many times the load testing comes when the application is already deployed. So it's like, okay, we're just going to fix some bugs, but sometimes you have to rewrite all the architecture to accommodate for the scale of the application. So first, there are tools to do the SharePoint load testing, even to generate the dummy data. So it's not the repeated data, but dummy data. Or you can even, if you're a Microsoft partner, you even have these Office 365, how is it called? There are pre-deployed tenants with a lot of demo data, so you can query against that if you're trying to test the APIs to get the data from SharePoint, just to see some metrics around it.
For instance, if somebody in the company or project says that you need to add like 10 new servers, is there a way to simulate that before you do the investment?
To simulate 10 servers.
Like, how do you make sure that the decision is going to be correct?
Okay. So you would like to know beforehand how many servers would you need? Okay. There are some guidelines on how much load can one server handle, but basically you test one server and you increase the load in a constant fashion, and you will see what's the breaking point for your application load, because the response times are going to be linear, and they go up. Then you will find the breaking point from one server. It's not as straightforward as that, but it's kind of order of magnitude. It gives you a rough order of magnitude, just to analyze the load testing data, find your breaking point in your application. Usually it's a clear pattern. It's like you have a constant load, and then it goes up. The response time will really up. You will find the asymptote. Okay. Any other questions? Okay. Enjoy your coffee then. Thank you very much.